Thank you very much, Alessia, and the other organizer, Matteo and Lucia, for this opportunity to present here this recent work that we have done in IRIM about let's say, quantum sensing and microscopy. The work has been done in the Italian, I work in the Italian National Institute for Research in Metrology, which is responsible for the maintenance and development of reference standard for the international system of units, but also the institute has got a lot of activity in fundamental scientific research and technology transfer. In particular, I'm part of the quantum optics sector directed by Marco Genovese, in which there are many lines of research, quantum imaging and sensing with photon that I will tell you about in the next slides. But we have also activity on sensing with color centering diamond, metrology for quantum key distribution, some, let's say, fabrication of the device, for example, transition and sensor, and we have a long-standing activity on quantum foundation. And if you are interested in one of these subjects, we have open position for postdoc and PhD students. So let's keep this. What I would like to is just to first of all to explain a bit better the title. So essentially, I would like to tell you about some example of quantum sensing microscopy that are based on photon counting measurement. Of course, all in measurement in quantum optics at the end is photon counting. But what I mean here is that we don't care about the phase, we only measure photon statistics, so we do not require interferometric measurement, and these allow to work with partial coherence of the light. We do not need phase preserving channel, and also we don't need sub-wavelength stabilization of the optical system. That can be useful in some practical application. So what I would like to present is, present are three different experiments. One, okay, the last one actually is a theoretical work, but essentially one is about quantum enhanced phase imaging, the other one is about quantum super resolution and microscopy, and the last one is about quantum LiDAR. Let's start with phase, let's say, with phase imaging. We know that most of the sample, for example, biological domain, are highly transparent and they present a very low contrast in transmission microscopy, while the structures can be revealed by phase imaging. In particular, as I mentioned before, we concentrate on non-interferometric imaging techniques in which the phase is revealed by the propagation effect that it has on the intensity section. Still, we want to extract some quantitative phase information in the sample. Okay. So essentially, okay, so the one of the non-interferometric technique which is using classical, let's say, imaging is the so-called transport of intensity equation. The idea is very simple. Okay, if you have an imaging system and you have a detector, if you place a pure phase object in the conjugate place of the detector, conjugate plane with the detector, you don't see nothing the same. But if you move the object a bit far, in this case the object a bit with respect to the display, you can see some effect on the intensity. You can displace forth or back now, okay, and you can, for example, extract some information. Well, information that one can extract that is useful is the derivative, essentially to estimate the derivative of this intensity, how this intensity changes with respect to the position of the object. And with this information, this equation tells you how to obtain the information, the gradient of the phase. One can solve this equation and the the solution of this equation, sorry, well, the solution of this equation is unique and quantitative, and is also applicable in with partial coherent illumination. We don't need a full coherence to extract this kind of information. This is very useful for what I'm going to tell you after. Okay. I will use this. Okay, okay. Well, okay. One problem, of course, is that especially when you deal with biological or a delicate sample, you don't want to exceed in optical power and not to disturb the process that you are going to investigate. But decreasing optical power can introduce some effects, for example, the shot noise. And quantum correlation in this case can help. So what we have done is to combine the, let's say, the phase imaging with the transport intensity equation with a very old technique that is called structured noise imaging that exploit essentially the spatial correlation among two beams produced by spontaneous parametric conversion, for example. And in particular, it works in this way. So we put the object in one of the two beams, and we obtain the image, let's say, classical image of the object in one beam. But we use the noise pattern measured in the other beam as a reference to remove the noise from the intensity measurement. So we apply the transport intensity equation, but with the substitution of the intensity with the correction performed by the measurement in the reference beam. And this allows to get a better quality of the reconstruction of the phase, essentially. These are one-shot measurement. We do not require raster scanning. This is made in a single shot, or actually two shots, because we need to evaluate the derivative by putting the object into different positions. But in principle, it can be done very quickly. So these are just some comparison, some say quantitative evaluation of the quantum advantage that we have. We have two figures of merit, for example. One is the Pearson correlation coefficient with a target image, and the other one is the uncertainty in the phase estimation, and both provide a good level of, let's say, signature of quantum announcement. More recently, okay, we have done some step forward. In particular, we have considered not only phase, but phase and amplitude object. This is a nanofabricated mask that contains both phase profile and absorption profile that are, let's say, overimposed. And we can, let's say, separate the two information, the transmittance and the phase, with very well accuracy. And so the method is really working for real sample that has got probably both the things. Another important step that we have done recently, that we have recognized that was possible by the sort of synergy between structured noise imaging and transport intensity correction, get rid of one of the main drawback of structured noise imaging, at least when you want to do it wide field, that is the trade-off between the quantum advantage versus the resolution. I don't have time to spend too much on this point, but I would like just to show you that, let's say, this is the quantum advantage graph versus the resolution. This was what we obtained with, let's say, previous measurement, in which you see the quantum advantage is very, let's say, dependent. You have to give up some resolution in order to get a good quantum advantage, while now we can basically decouple the things, and we can have a good quantum advantage independent from the resolution that you want to achieve. And this was enough for moving towards realistic real samples. We have here the image of cells, OVA cells from this guy here, and the different step of the evolution. On this column, you see essentially an image which is average over many frames in order to remove noise and artifact, while Here in the central column, you have the classical frame in which you see some distortion of the information that you have on the sample, while in the quantum frame, you see that the information is more faithful with respect to let's say the target frame. Even though here the color are a bit changed with respect to my computer, and since the effects are less visible, but we have measured a 20% of enhancement in this case. So this is the first. Okay, oops, I forgot that. This was interesting, but of course we need to make a further step in order to improve the technique. For example, increasing the resolution by changing optical system and essentially probably increasing also the optical power that we use. But we hope to have the possibility to do this in the future. Now, I would like to move to another problem of imaging, which is the one of the resolution. Of course, we know that in optical imaging, there is a well-known limit for it that is due to the diffraction. In particular, in microscopy, you have the Abbe criteria that states that you cannot distinguish two point-like sources if they are closer than this distance, which is determined by the wavelength of the light and numerical aperture of your optical system. However, this is not a fundamental limit. There are some assumptions behind, for example, far-field measurement, intensity measurement, uniform illumination, and linear response of the sample. If you can break one of the assumptions, you can hope to achieve super resolution. Okay, there are many ways to do this. In part, I select two of them. One is, for example, structural illumination microscopy. In this case, you break the assumption of uniform illumination. Essentially, the trick here is that if you have a sample with high frequency, spatial frequency that cannot pass through the optical system, essentially you can convert down to the lower frequency by beating, let's say, the frequency of the sample with the illumination pattern, and this can get a factor 2 of quantum, of super resolution. But there is another technique quite recent, which is essentially improve the resolution by not only measuring the intensity, but also the photon statistic of the light. Okay, and in this case, you can improve the resolution with respect to the diffraction limit of a factor square root of j, where j is the higher order of the correlation or the highest moment that you can measure of your photon number distribution. I would like in this slide to give you some hints about how does it work essentially in the case, for example, of single photon emitters. If you have two single photon emitters that are placed closer than the diffraction limit, they emit photon one by one. If you wait enough time, of course, you can integrate the photon flux, and for example, if you have single photon counter or intensity measurement, you get a blobbing, you cannot distinguish the presence of the two emitters. While if you can measure, for example, the coincidences in the arrival of two photons at the same time, you have some chance in between the two photons to get one photon from an emitter and one photon from the other. So the coincidences are not zero. While if you sit more on a single emitter, you can get almost zero coincidence. So you can, with the second order Glauber correlation function, which is nothing else than a measurement of the, let's say, normalized coincidence, you can get information on the internal structure of this block. You can see here. And with this information combined with the intensity, you can get some super resolution map. At the second order, you have to combine the intensity and the second order correlation in this way to obtain the super resolution. But you can also extend, increase the super resolution to a factor square root of j by increasing the number of, let's say, detectors, or making a j-fold coincidence, or if you are lucky, if you have money, maybe with a photon number resolving detector. Okay, There has been this technique has been applied in already in wide field microscopy, in confocal microscopy in our group, and image scanning microscopy. So it's quite consolidated technique already. Don't be scared about this slide. Just to tell that recently we have developed a general model which is able to extract the super resolution map, what we call QSIPs, from the framing of these by essentially for whatever distribution, photon number distribution of the emitter. So we don't, not only for single photo, you can have super Poissonian light and so on. The important thing is that is not Poissonian. But for example, in fluorescent microscopy, is not the case that you have Poissonian emitter. So essentially, this works just by properly combining with this coefficient. This can be derived the cumulants of the detected photon number distribution up to the order J. And this is our experimental setup. Is a standard fluorescence microscope with the different. Just here we put a spatial line modulator for generating spatial pattern. The sample that we consider is a planar distribution of a blinking quantum dot that provides certain, for example, super Poissonian statistic, but can also you can also go, say, for sub-Poissonian statistic. Anyway, one of the important things of this setup is that we measure the light with a camera which has some photon number resolving detector features that is allows us to get more precise information about the photon statistics. Okay. And these are the results. Essentially, this is a simulation in which we have essentially used the same parameter of the experiment. Here you have the diffraction limited intensity image. You cannot recognize essentially what is there. If you use just the photon statistic approach, you can improve a bit your resolution, but if you combine QSIPs, sorry, I forgot to say an important thing, I will come back. But if you combine the statistic with the structural illumination, you can really appreciate the location of each emitter that has been put here. Okay, from the experimental point of view, we were not able to, of course, to create, let's say, an array, a well-determined array of position like that. We have a cluster, we identified a cluster, but you can see that with QSIP and SIM, you can obtain more or less the resolution that you expect from the theoretical point of view. Okay, I forgot to say an important thing, that while we are interested in combining the structural illumination and photon statistics, because actually, it has been proved that if you combine these two techniques, the advantage that we have in terms of the resolution, scale J plus square root of J, where J, I remind, is the, let's say, high moment of the resolution that you can measure. And this is a very powerful scaling, which is more than just the sum of the two advantage. Okay, and this is really interesting for application. So this is some that we and so this is why we obtain this beautiful increasing of the resolution. Okay, so now I would like to move to another technique. We move from the microscopic domain to the long range, let's say, detection. In particular, I would like to show you a work that, but it is only theoretical at the moment, about quantum LiDAR. We know that LiDAR, light detection and ranging, are very powerful tools for many applications, for surveillance, for autonomous vehicle navigation, environmental monitoring, and so on. And one, of course, people has been considering since many years ago to improve this kind of task by quantum resources. Okay, the first attempt is probably the quantum illumination approach. In quantum illumination is a binary hypothesis test in which we have two hypotheses: or the target is present, or the target is absent, and you have to decide which is true. And of course, there is an error probability associated with this task. The scheme can be represented here. You have a state of the transmitter transmits a certain number of photon west to the target. You can use essentially transmitter many times, m times, and the target reflects back some part of the photons. And also at the receiver, you get some background from the environment. Okay. In this situation, it has been shown that if you can rely on an ancilla system, which is entangled with the probe beam, what you get is a 6 dB quantum advantage in this factor, xi, the error in the probability exponent. And of course, this is quite a large improvement that has triggered a lot of work, a lot of study on this, on the quantum illumination subject. But unfortunately, till now, I mean, the quantum advantage is only found for a very small photon number of the transmitter, very small reflectivity of the target, and a lot of background photon. That means in practice that your signal noise ratio is really poor, okay? And it's so poor that is completely non-practical. So the advantage is found in a region in which there is no practical, let's say, advantage, even though, I mean, in principle, you can get an advantage. But and there are other drawbacks. For example, the optimal receiver requires quantum memory to store the auxiliary mode, and phase preserving channel, which is a rather not fulfill condition in practical case, especially for LiDAR. Then the target distance is not assessed in quantum illumination, so it's only about the LiDAR. You have only light, but you don't have R, because and so we miss something. What we wanted to do is to try to solve some of those drawbacks. First of all, we have considered a scheme for target ranging, in which the object can be in one of different distance from the transmitter, and this means that the returning signal can occur in one of different time beam at the detector, and so basically our task is a multi-hypothesis test. We need to guess in which of the cell is possible to, the object is present. The resolution of our scheme is fixed. It's kept fixed by, for example, the time jitter. One can think to be fixed, for example, by time jitter of the detector. And we also consider that the phase information is lost. One can also make it lost by purpose, but okay, it's lost, and so only photon statistics, photon counting measurement can help to recognize the task essentially. We discover first of all that the information that you have on target range is in general larger than the information that you have on target detection. So it's a bit easier task, target ranging with respect to target detection. This is valid also for whatever measurement, okay? Also for the best POVM you can do. While if you fix the photon, the measurement of the photon counting, and you fix the power of your for the comparison between classical and quantum, what you get is that you can have an advantage which scales as 1 over mu, essentially. So for small number of photons, you can get also, by fixing this measurement, a quite large quantum advantage. And of course, we use, as usual, two-mode squeezed, a certain number of replicas of two-mode squeezed vacuum as a transmitter. for getting this quantum advantage. As again, even in this case, unfortunately, the quantum advantage is still in the regime of small number of photons. Thank you. That means a small signal-to-noise ratio. So, okay, we need some motivation to go in this regime, okay, because otherwise quantum resources are not useful too much. A motivation can come from the cover sensing. Cover sensing means that there is Alice that want to detect the presence or the distance of the target, but there is also an adversary, Eve, that can catch the photons that are not reflected back and to make a measurement to detect the presence of Alice. And Alice wants to avoid to be detected. So this is cover sensing. In cover sensing, we have essentially, so we have to compare the Alice information about the task of ranging, which is, let's say, active in the sense that Alice can send a probe and as the control over the parameter of the probe, while Eve can say, perform a sort of binary decision, so a sort of target detection, but he doesn't have control on the parameter, and he can extract some information. So we see that, I mean, we declare that the cover sensing condition is obtained when the information that Alice has on the target is larger than the information that Eve has on the presence of Alice. And these are the results, essentially. If you, in this case, I consider a technological evolved adversary with the efficiency of the apparatus equal to 1. In this case, I mean, if you plot the Alice information versus Eve information, you see that you can do coverness only if you are above this black dotted line here. And the quantum probe can ensure coverness because it's much higher than this line, while classical probes, for example, coherent state as a transmitter, are below the covert regime. So in this case, with this technologically evolved adversary, with quantum classical light, simply you cannot do cover sensing, while you can do it with quantum light. The second point that deserves attention is the fact that even if you consider a quantum transmitter, the advantage that the coverness is found basically almost independently on the number of background photons, only when your signal photon is in a certain range, which is typically very small. So this is the real justification of using a small number of photons. If you want to do cover sensing, you need to stay in the low photon number regime. This is a plot that represents the error probability of, with respect to the number of usage of the probe, and you see that essentially the blue curve represents the error probability for Alice in target ranging using quantum approach, and you essentially it can be make it as small as we want, essentially, while is a bit less than the one of Eve. So in principle, you can do some cover sensing, but of course, it's much better to use quantum resources, even for, let's say, small detection efficiency of Eve. So this is what I wanted to tell you today. I would like just to finally to thank the people that has been involved in this project, in particular Giuseppe Ortolano, Alberto Pagnata, and Fabio Picariello, our former PhD student that did main part of the job. We have for phase imaging a collaboration with two Delft, in particular a group of Silvano Pereira and Sarika Soman, and we have also a collaboration for cover sensing with Leonardo Banchi of the University of Florence. I would like to thank you for your attention, and I leave you with the summary of what I presented. Thank you very much.